Hello, this is Anthony Schmitt. This is for ME3708 Machine Design 1, Section B. And today we're going to do the video topic 1. And so let's get started on that. Slideshow. Alright. Now, sort of an introduction to machine design. Machine design is a basis for engineering. We engineers are problem solvers, and part of being a problem solver is understanding those fundamental theories and then finding applications for them, and that's what this class does. It shows us applications for all these theories and all the knowledge we have on engineering. It allows us to apply them and get us ready for real jobs. There's a number of mechanical design topics we're going to get into in this course. Static and fatigue failure theories. We're going to analyze machinery components, which could be with shafts, fasteners, bearings, springs, gears, for example. And we're going to learn the design of mechanical systems, and one example of that would be a gearbox. So, in engineering design, there are some requirements. First of all, it has to be physically possible. As engineers, we got to know what we design can actually be used. And it also has to be economical. We got to know if this project that we're designing is even worth it. And third, but definitely not least, is safety and standards codes. We got to take care of the environment, and we got to take care of each other, and we got to make sure our projects don't hurt either of those things, because that's the sole purpose of living, you know. Now, one of the most important things for engineers is failure. Failure could come in a lot of ways and different things. Deformation is an example of failure. There's elastic deformation, plastic deformation, and creep. And an easy way to remember elastic and plastic, the difference is elastic is like a rubber band. If you stretch a rubber band, it's going to go back to its original form if you let go. Same with elastic deformation. If you deform something elastically, it'll revert like a piece of metal, it'll revert back to its original shape. With plastic deformation, think of, say, like a plastic spoon. If you bend it, it's going to stay bent. And that's how it works for plastic deformation of metals. Creep is from long-term stress that causes that deformation. Another kind of failure is fracture. Brittle fracture means there's no prior deformation to the fracture. It just breaks without any signs of deformation beforehand. Ductile comes from extensive deformation, so where it's deformed so much that it eventually breaks. And then fracture can also come from creep, and then fatigue is like many short-term stresses over time. So think about if you get shin splints from running, that's sort of like a fatigue fracture. It's because over and over again you're running, putting stress on your shins or legs or wherever, and it causes a fatigue fracture. So our jobs as engineers, we got to understand failure mechanisms. When we understand those, we can predict the failure, and we can design our projects to prevent failures. So the main topic for today is energy methods. Energy methods are very useful in certain applications where you don't necessarily know certain parameters in a problem, an energy method is an alternative method for beam problems and such. Keys to success for energy methods: you gotta know how to calculate deflection on complicated geometries. In the real world, there's going to be complicated shapes. It's not going to be like an engineering problem like you would in a class. It's going to be all kinds of crazy different shapes. You got to know how to take on these different shapes. It's good to know the benefits of energy methods. We'll get into that in the next couple slides. You got to understand strain energy because it's important in energy methods. And our main focus here is thin curved beams. We've all seen and dealt with straight beams, but curved beams is another story. See, these kinds we've all seen in our classes with statics, Mechimat. But this is what we're getting into with energy methods. Energy methods allows us to solve beams like this and different problems. So the benefits of energy methods. It's another option if certain details are left out. So it allows us to solve the problem without the information that we might need for our standard statics way of solving. You don't have to solve for a set of auxiliary equations to get the solution, and you don't have to solve a full system of equations like you would in without energy methods. So the main tool in the energy method is Castigliano's theorem. We use this theorem to calculate deflection under forces. So the definition of Castigliano's theorem is the displacement corresponding to any force in the direction of the force is equal to the partial derivative of the total strain energy with respect to that force. So we can see that here. We have the deflection equals partial derivative total strain energy with respect to the force. And one thing that we utilize with Castigliano's theorem is fictitious forces. That's something that we place in the direction of the deflection and use it to solve for the deflection. We have to know the bending energy, and we use the Castigliano's theorem to solve with various geometries. And so long as we keep with Castigliano's theorem's rules, we can solve these different complicated geometries. So we need to know the total strain energy, and there's a number of different ways we can find that. There's a number of different equations. So for tension and compression, we have these. If we have bending, we have these. If we have torsion, we have these. And then transverse shear, we have these equations. However, if we have a curved member, it's a little different. A curved member, if you apply a force on it, it's going to result in 4 strain energy terms. And that's from this radial force, this moment, this axial force, and then the force. Just the excuse me, the applied force. However, as R increases, bending component dominates all other terms. So we get these equations here, R over H greater than 10 for the strain energy and the deflection. So we have a basic procedure for solving these curved member equations. or problems. First, we want to divide the beam into segments, and there's never a correct number of segments in each problem, but there is a better number of segments. It depends on what you're looking at and how the problem looks and how many different geometries there are. And so we want to know how to divide it up correctly to give us the easiest solution. We then place our fictitious force Q. Should be where the deflection we're trying to find is, in the direction of the deflection. Then we calculate the moment for each segment. We do a moment sum with the forces in the segment that we're looking at. Then we calculate the derivative of m of the moment, and we use those to find the deflection. So let's take a look at this example. We have a cantilevered hook. It's formed from a round steel wire. It's a diameter of 2 millimeters. Hook dimensions: L is 40 millimeters and R is 50 millimeters. Force P of 1 Newton is applied at point C. Use Castigliano's theorem to estimate the deflection at point D at the tip. So we're trying to find the deflection at this point D. That's going to deflect down. So we're going to use Castigliano's theorem to find that deflection. So let's look here at the example. We have our beam. So we say we want to find this deflection here. So we apply the fictitious force Q. And Q is what we call it. Then we divide into our sections. We have section 1, section 2, section 3. Okay, we look at section 1, and we have this moment here and our fictitious force Q. We sum the moments. M, sum of moments is 0. M plus Q times R minus R cosine theta, which is the moment arm there, and that's equal to 0. So we have M equals negative QR times 1 minus cosine theta. Then we move on to the second one. It comes from point of deflection to the other side of this force P that we had up here. So first segment was here within this radius. Second segment goes past and it includes the segment before. So, excuse me, we have the sum of moments equals M plus PR sine theta, the force P, plus Q R plus R sine theta. So then it's this moment, this force P, fictitious force Q. We have M equals minus PR sine theta minus QR 1 plus sine theta. So then we move on to the third segment, and this time we're at a linear portion, so we can take it in X and not in theta, which is what we did up here. We used this theta here and this theta here. Now we can do it in X, and we can say this moment, M, is equal to minus P X plus R. We have the X plus the radius, and then minus Q 2R plus X, 2R plus X. And that's our moment there. So from there, what we can do is make this table where we show the moment. We have segment 1, segment 2, segment 3, and then the partial derivative of the moment with respect to fictitious force Q. We have those there for all three. And so the deflection total deflection is what we want. It's going to be the sum of the deflection from segment 1, segment 2, and segment 3. Let's turn the page here. So as we can see here, for deflection of segment 1, it's the derivative from 0 to pi over 2, which is that portion that we cut off for the segment. And it's m over ei times the partial derivative of m with respect to q, r d theta. And we know that that m is 0, so this portion of the deflection is 0. And so then we do the same exact equation here for segment 2. Excuse me. So we know segment 2 is also on this curved portion. So we have 0 to pi over 2, 1 over ei. Then we have the moment, PR sine theta, times the partial derivative with respect to q, r, 1 plus sine theta. We solve, we get this. And then section 3, we have the derivative from 0 to L, because remember section 3 was on this horizontal portion, this linear portion. So we say 0 to L, 1 over e to the ei, the moment, p, x plus r, times the moment, derivative of the moment with respect to q, x plus 2r dx. And then we solve this out. We get this for the third segment, and then we just sum our deflections here, as we did. We got 0 for that one. That's segment 2, segment 3, and boom, that's our total deflection.